Chapter 8 is on techniques of integration. And so we already know how to integrate a few things. And now we're going to look at a number of techniques and concepts in more integration. So first, I wanted to go over just some background 8.1 on the basic formulas you need to know. And this is just one table that has the majority of the ones you need to know. So primarily these over here, and then you get into the little more complicated ones. But these are what they call the basic integral formulas. And so the ones you just have to flat out memorize, I would say, are, here, I'll just highlight them, I guess. Okay, so let me just fix that. So I would say are, put it in red, obviously number 1, number 2, 3, 4. Now 5, you don't have to memorize that one. You can basically change the base and figure it out differently. I'll skip that one. It's basically derived from 4, but 6, of course, 7. And then you're getting into these, which you definitely need to know basically the derivatives of these. And so, okay, so these are the ones so those one you have to know, okay. And I mean, you can't go through calculus without knowing those by heart. The rest, you have to have a really good familiarity with. I'll put it in pink. Okay, so these, you need to have a good familiarity, you need to know what they are, basically, that you recognize them, know basically what they are. Okay, and then, of course, these you got to know too, geez. So 16 and 17, sinh and cosh, pretty easy. And then you need to recognize the rest of these pretty well too, 18, 19. And then you get into this, so, when you're looking at this here, so these are if you look at these, you can translate those in either way. How come those look? Oh, one has a root, one doesn't. Okay, so this is what I was looking at. So that has a negative, that is a plus. So recognize the difference between those two. Okay, so the ones in red, you just have to know. Okay, the other ones you have to be familiar with. So it's like, the analogy I like to give is, let's suppose you're trying to get from, your house to another city, and it's down here, trying to get to your mom's house or something. And they just moved. They just retired, so they moved. And so you're trying to get there. It's much easier, I'm sure many of you have done this, if you look up online or a mapping system to where you can kind of see where the streets are and how to make the turns. Now, you don't have necessarily a memorization of exactly when to turn, but you know that you've seen that, McDonald's here on the corner, and so you're close when you see it, right? So you don't know exactly, but basically that you take off and then you're going to make a couple turns, and then you know that there's a few turns in here to get there. If you look ahead of time and you have a basic understanding and familiarity with it, you will get there much faster. You won't have to when the GPS tells you to go this way and you're not supposed to, you need to know that you're going the right direction. Okay, so a little bit of background research does a long way. That's what the rest of these really, I think, are for, is you need to know what those are, at least close, so that you can recognize, oh yeah, that looks like sine inverse, or that looks like a sinh, because you have a plus down here. Some of you are really good at memorizing, and it's not going to hurt to memorize all of these as you go. It makes your work a lot easier. So hopefully that made sense to you. It's an analogy I always like to give in memorization concepts. Okay, but generally speaking, math is not about memorization at all. It's about basic concepts you're applying. And we're about to do another basic concept of what to do. So let's look at these techniques. The chapter 8.1 is really just on like just some more stuff to look at, more stuff to analyze. So let's take a look at these questions. I have a few down here. You can see, you can copy those all down if you'd like and pause. These are the ones I'm going to be doing. Okay. So this one doesn't have a form we're really familiar with. It doesn't match any of those above. Okay. However, what you can do is you can complete the square. Oops. You can complete the square. So you take your 8x minus x squared and you complete the square on that, which is equal to, so first thing I'm going to do is factor out the negative and rewrite this as x squared minus 8x plus 16, like that. Now, before I continue, maybe look up how to complete the square. So here's the idea. I don't memorize how to like what this would be, right? I mean, you have a technique to complete the square. That's what I'm going to follow. So, oh wait, I went way too far. Pretend I didn't write that down. Okay, so pretend I had that. So what you're going to do is say plus something. I went way too far on that. And then you want to balance that whole thing. Okay. So what you do is you take half of that and square it, right? So you take half of the 8 and square it and you get 16. So you're going to add 16 here. And what did I actually add to it? I actually added negative 16. So I must balance it with a positive 16 over here. Okay, so that's what you have to do. I'm going to go ahead and get rid of this, just you'll be able to remember that. And so that's a perfect square trinomial. It's negative, and that ends up being x minus 4 quantity squared plus 16. Or we'd want to write that as 4 squared minus x minus 4 quantity squared. So there's the negative right there in the middle, and it is the correct format. So you rewrite this as the integral of 1 over, and that's the square root of, and then you put that in there. So all of this goes in the radicand. Whoa. All of this goes in the radicand. Let's try that again. I was going to just copy it because I can right there, and I'll just extend this over like this, like this. That's a dx, and so you get, this is equal to, and so what you have then is, this is your a, so basically you're going to use a formula. So a is equal to 4, and your u would be x minus 4. And so then if you look up here, you can see what you have. That must be which form? It's 1 over, and then here's an a squared minus x squared. So it's this form. And you would have to do chain rule on that, but you just get 1. So your du is just dx. So nothing to do with the dx part here. Because we're all good to go because that's x minus 4. And so that's equal to arc sine or sine inverse of, and it's the u or x minus 4 over a, which is 4, and then plus c. So you apply a formula. In this case, it was, I don't think of it as 1 through 21. I mean, obviously, you're just going to think of it as that's an inverse sine. So inverse sine, I mean, this one really can be read here. I mean, you really need to know inverse sine, case, and inverse tangent. Those are the ones that come up a lot. Those other ones, not so much, but you just need to know the right order, because right away, if you do a different order and you make one plus or negative, it becomes sinh and cosh, or inverse sinh and cosh. All right, moving along. Let's see. I think I've got enough space to do that one up there. I'll go ahead and move this one up. That's just my spacing. You don't have to worry about that. All right, let's try that one. So this one, you basically want to multiply that out. So you want to multiply it and then simplify it with identities. So I'll just write down make use of trig identities. So multiply it out. I'll write down secant plus tangent squared, and then we want to do the product. I'll zoom in a little bit, make it a little smaller. So the product will be secant squared x plus 2 times secant tangent, and then plus tangent squared x. So, right, that's just how those multiply out, of course. But we can convert tangent squared into secant squared minus 1. We can use that use a trig identity. So a trig identity gives us secant squared x 2 secant x tangent x, and then make that a plus, and that'll be secant squared x minus 1. So now we have just converted this using a trig identity. And I also wanted to mention, while I'm thinking of it, in the Files menu on Canvas, you'll find a Formulas and Tables. I'm going to rename it to say Formulas and Integral Tables. It looks like this. And I believe it's like int form int form geo or something like that. I'm going to rename it though. It's Formulas and Integral Tables, which also has derivatives too, but it's a real, I like this one that's formatted. It has all the geometry here. It has some trig. We just used which formula? We just used this one here. So secant squared, or no, tangent squared is secant minus 1. So, and then it has a nice unit circle. And then, of course, so you have a unit circle there, double angle, power reducing, all of these you use a lot. After that, they're a little more obscure, but just, need to know they exist. Then you get to the derivatives. So this is the derivative basic formulas. And then here's the basic formulas for this book. Pretty much, I'm sure, will be similar. Yeah, I like this one better, actually. This one has all the main stuff here, and then cosine, sine, tangent, and then then it gets into the other ones. And then this has other tables as well. We'll get into integral tables on this. So again, more basic formulas here. And then it gets into the different forms where you have x squared plus u squared, etc. So tables we'll get to in, I forget what section, but that's where we're heading. There's all of these. You can download this if you want. It's one of my favorite ones from an older book. I just like it better. Okay, let's continue. So now you can write that as 2 secant squared x plus 2 secant x tangent x minus 1. And so when you do that, it becomes your integrand, and we can then integrate a little easier. So that's equal to integral dx. And so now we're just doing secant squared and secant tangent, which, so if you go back up here, we have secant squared and secant tangent. Now it's a form we can use, and then of course just a constant. So this equals, you can use those tables, write down what it is. That's equal to 2 tan x plus 2 secant x, and then that's just minus x plus your arbitrary constant. Okay. Moving on, let's do the next one. It's bring this one up here. Okay, so here's the next technique. Let's take a look. So this one might tip you off. This power is 1 higher than the denominator, so we use long division. Okay, so I'll just say use long division. And I didn't show it. I'd better do long division. So if you use long division, it's 3x plus 2 divided into 3x squared minus 7x. So you say what times 3 is 3x squared, and that of course is just x. Let's change colors on this. You multiply and you get 3x squared, of course, plus 2x, and then you subtract. You draw that and you subtract. And then you get that's 0, of course, and then that becomes a minus, and you add 7, 8, 9 becomes a negative 9x. And then you ask the question, what times 3x is negative 9x? And that, of course, is negative 3. So minus 3. And we get, okay, so you get negative 9x, which is what we wanted, and minus 6. Okay, and then you subtract. That's 0. It becomes a 6. So your remainder is 6. So what we can say then is that this is all your long division stuff from algebra. This is equal to your quotient, x minus 3, plus your remainder over your divisor, which was 3x plus 2. So that's our basic technique, and this now becomes your integrand. Let's duplicate that and bring that up. And that would be a lot easier to integrate. Now we can do it. So this is simple, and then what is that? Equals, and so you you integrate, and you get 1/2, oops, we are actually integrating. Let's now apply the integral, and you get 1/2 x squared minus 3x plus, and let's go ahead and do this one out. So if you pick your u, let's see if I have room here. I can just do it down here. Okay, so let's just let u equal 3x plus 2, then du is equal to 3dx, or du over 3 is my dx. So I will reduce that a bit and substitute. So by doing that, I get 6/3 times the integral of 1 over u du. And now do you recognize that? That is natural log, right? Okay, it's equal to 1/2 x squared minus 3x plus, that's just 2 ln, and it's absolute value of u, but u is 3x plus 2. And so it's all that plus my arbitrary constant c. I knew this was going to get in the way eventually. Let's put it up here. Sorry about that. We'll just rearrange this. You can look at it for later. So that's what we get when we do our substitution. My scratch work, my research was all in the way. this time. All right, I'll try better. I'm a little rusty. All right. So, another type of technique. Let's do another one. So next one is this. So this one, really, maybe you can recognize like what you might do is you can take this denominator and divide by each term. So by doing that, you have the integral, and then it becomes 3x over square root of 1 minus x squared dx plus the integral of 2 over square root of 1 minus x squared dx. So the first one, so try that one, but the first one, well, okay, spend a second to think about it. Do that, see if you recognize any forms back to our basic integral formulas, and you should. So here's one, right? Here's an a squared minus b squared, or I'm sorry, a squared minus u squared. 2, of course, just factors out. So that's a sine inverse again, a minus your x squared. So this is just sine inverse. What can you do with that? Yeah, that's just basic u substitution. If you pick your u to be this, you'll have your 2x. Well, here's your x. So that's what you get. So if you let u be 1 minus x squared, then my du is negative 2x dx, or I can write that as negative du over 2 is equal to x dx. So I make that substitution, and I get the 3 over 2, oh, and this negative, let's put a negative in front. And inside then will just be 1 over square root of u du. And then this next one we already know. This one we have that a is equal to 1, and then my u is just x. So that one's pretty straightforward and easy. Well, I mean, once you see it, I guess. So that's just 2 sine inverse of x plus c. And this one, the negative, let's see. I messed up somewhere. Maybe I didn't. Well, let's just continue. So we have, let's see where I'm at. Negative 2x, that's a 3. Okay, that one's done. X, factor out the 3. So u to the half, add 1, right? So what does that end up being? So integrate the root. So we're doing integral root u du, integral of u to the half du. So you end up adding, so you get 1/2 plus 1, 1/2 plus 2 over 2, so it's 3/2. And divide, so it's 2/3. 2/3 times u to the, excuse me, 3/2. plus c. So this ends up being, my integral is wrong there. This ends up being, oh no, that was negative. Okay, let's try that again. That was negative. We're doing the integral of u to the negative 1/2 du. Okay, so now that's u to the negative 1/2 plus 2 over 2 over whatever that is. So that ends up being 1/2, so it ends up being 2. So this becomes just -3, and that becomes u to the 1/2. So when this will then reduce, because this ends up being on the top, and so you just end up with a -3, and then that's the square root of 1 minus u, which is x squared. And then 2 sine inverse x plus c. Okay. I'm sure most people would probably redo that, but I want to show you that sometimes you got to think through it and figure it out. All right, next one. This will be the last one we do. Any ideas? I don't know how you think of this, but multiply by 1. This was like, really? This is how it works? Yeah, this is how it works. It's kind of a trip. If you multiply by e to the negative x over e to the negative x, which is totally legal, right? Because e can never be 0. And so for any power. And when you do that, you'll get a form you can reduce. It's pretty cool how this works. I would tell you this sort of thing, but still, it's a technique. You can always add 0 or multiply by 1. And 0 would be in the form of like, a minus a or something. So you get 1 over 2e to the x minus 3, and then you multiply by e to the negative x over e to the negative x. By doing that, you get e to the negative x over, and then this becomes just 2 minus 3e to the negative x dx. So now let's do try your u substitution. So let u equal 2 minus 3e to the negative x. Then du is equal to, that's 0, and that becomes just positive because you do your chain rule, 3e to the negative x dx. Well, looky there. Here's your e to the negative x dx, e to the negative x dx. You will be able to substitute that directly. And so you have du over 3 equal to e to the negative x dx. Wow, isn't that awesome? That is so cool how that works. All right, so then now we substitute. The 1/3 just comes out, and then that ends up being the integral of 1 over what? What does it end up being? So that's just u, and that's just, that's du, including the third. And that becomes just u. So that's just 1 over u du. So that's equal to 1/3 ln opposite value of u plus c. And then now let's substitute for u, and we're done. This one was like a really cool one. I don't know about you, but then you get natural log opposite value of 2 minus 3e to negative x, and then plus c. All right. So we've had a number of techniques here. Can't let that. Trying to get this to go away. I can't get it to go away. Go away. There. All right. Just a quick recap, because this is a long video. So basic integrals you need to know. One concept technique is complete the square. You have trig identities. We'll look more at trig identities later. Use of long division to simplify if you have one higher than the bottom. It expands it out in a nice way. Then we have separating the denominator, right? Separating the rational expression there. Okay, and then you have this multiply by 1 or add 0 concept. This one, it just happens to work. So something you can try. Sometimes you go down the wrong path and it's not going to work. Okay, so you want to get used to just, it's not always one path you go. It could be, you could end up stopping and then trying a different path. Okay. Integration by parts is next, really important one.